Simone Marras from Barcelona, who's going to talk to us about work he did for his PhD.
Hi, thanks for coming. Yeah, I will show you some results on the application of finite elements with variational multiscale stabilization to solve the Euler equations coupled to transport equations for water tracers in the atmosphere. So the idea is that of trying to simulate, it's kind of a proof of concept, but the simulation of convective storms and convective dynamics. This work was actually is part of my work during my PhD, and I was supervised by Mariano Vázquez and Oriol Jorba, and partially worked with Guillaume Musso and Margarida Moragues as well. Margarida was here for the PDEs, and she showed a few results from this presentation as well, at least on the dry dynamics. So what we are solving here in terms of dry dynamics first, and then we will switch into moist atmospheres. We are solving the Euler equations, and we are interested in solving them with respect to density, total density, momentum, and potential temperature. You will probably notice how we have momentum in conservation form, but we don't have a fully conservation form for the entire system. In fact, the equation for potential temperature are written in transport in its transport form for reasons that are mostly related to how we build variational multiscale for the transport part of the problem. We showed in a past talk a few weeks ago on how to apply this type of stabilization to the spectral element solution, the spectral element solution of advection diffusion equations, and so it's kind of an extension into coupled problems with them in the Euler equations for I thought this was on 60.
Get the frequency.
Right, but the frequency was supposed to be 60 at least, but now I can't even see what the frequency is here. Okay. Oh, here. So 60 standard. Is there anything I should change here? Sorry about that.
Someone's gone to get the technician. No, don't worry.
That's it. Hopefully it lasts until the end. So we solve them with respect to the total variables, and except for the fact that since we have an hydrostatic balance, the equations are for hydrostatically balanced atmospheres, we obtain a perturbation for pressure and for density in the hydrostatics term. Perturbations with respect to a background state that is time independent. So we are all pretty much familiar with this for now. We would like to solve them with finite elements, and why variational multiscale stabilization? Well, why stabilization at all in general? The point is that finite elements, when they are used to approximate problems with advection problems or problems with important transport, are actually unstable. If there is not enough diffusion, either physical or artificial diffusion, on some added in some way, we expect some spurious oscillations, some spurious modes in pressure and in many other variables. This either having this is specifically because we are using this is a collocated type of discretization that we are using. I'm not using any type of staggering, and probably some pressure modes could be avoided by doing some staggering, but we are not interested in using staggering in the solution of these Euler equations, although we are at low Mach number flows. So simply in a Galerkin approximation, and without even thinking of being in a discrete space, we project the original PD that is written in a general form as Q times LQ equals the right hand side, and we multiply everything by basis function. The space of basis function that we're using here is that of Lagrange polynomials, bilinear Lagrange polynomials on quadrilaterals. In a finite element fashion without stabilization, or at least without variational multiscale stabilization, once we go into a finite dimensional space, Q, the vector of the unknowns, would only be approximated with QH, which is the value of Q on the grid. In the context of variational multiscale, the multiscale idea comes into the actual splitting that we do on the solution, and we don't limit ourselves to approximate Q with QH on the grid, but also by keeping in mind that there are some values on the unresolved values that we cannot resolve on the computational grid, whose shape, mostly shape and contribution we don't know, but we don't know that they have certainly an effect on the solution on the grid space. So this is the entire idea of this VMS technique, which in reality can be it's very easy to see how under the idea of variational multiscale we can derive the classical streamline McGuinn Petrov-Galerkin and any other type of stabilization that rely on the use of additional viscous terms on the equation. I will come back to how we construct these subgrid scale terms that we don't really know how they are, what they look like, and we'll say something more about that in a second. The point is that if we plug in this splitting of Q into the variational equation in a finite dimensional space, we obtain the usual. Actually, here it shouldn't be with form. All these terms, just take it as a Galerkin term, the classical Galerkin, like I forgot to change this, and plus some term, additional term, this B minus S, where we have a function of Q tilde, or the subgrid case. Here I call it stabilization, but then you go and look at what this B looks like in the bottom square, blue square, and nothing is telling me exactly that this is in reality a stabilization term. Like here there is nothing that makes me think, at least dimensionally speaking, that there is some diffusion going on. Except for the fact that I yet have not said anything about the tilde quantities. So we have a tilde quantity in the mass equation, momentum equation, and the same for the transport equation. This is a result actually of integration by parts that was done in getting from the original equation to this point. So here there is an integration by parts in between, and that's why we have this nabla psi h that multiplies of this. To be able to have this additional term and consider that as a stabilization, viscous type of term, viscous-like term, we need to finally decide how to build the subgrid scales. It's not just a matter of assigning some value to these subgrid scales, by doing some, the subgrid scale term Q tilde can be derived in different ways. So we can actually write a system of ODEs for Q tilde. We can do some Fourier analysis on either on that system or some other initial definition. But the bottom line is that we get to, no matter how, from where we take the problem of defining Q tilde, we always get to an expression, or we would like at least to get an expression where the terms involved give you an information on the actual solution. So on the solution, in terms of equation, the original equation where the physical information of the problem that is being solved is being considered. In fact, by using R, for us is the residual of the original equation, and this is what the residual look like for any type of equation. In this case, this is a system, and we multiply by a parameter tau. So before getting into this parameter tau, it is important to notice how this now, by plugging this Q tilde into B, and where we have these tilde quantities that appear, since we have some space derivative in the residual term, then clearly we are going to have some diffusion-like term that finally appears within the equation, because if we have a space derivative of the h quantities in here or in the mass equation and multiplied by this nabla psi h, that's what my diffusion, like dimensionally speaking, my diffusion term would look like. Now, this diffusion term, pretty much like it would be constructed maybe in hyperviscosity, in a hyperviscosity fashion. The main difference is that the viscous coefficient is not either constant or uniform. It also depends on the characteristic of the flow. It depends on the characteristic of the grid. It depends on the characteristic of the grid, for example, by introducing the dimension h along certain characteristic direction of the flow. It depends on the flow by means of the modulo of the velocity. Then the main idea here is to have some diffusion term that is not either uniform, is not constant, but only is activated in some way where it is really needed. And this either in the context of simple scalar equations or a couple problems like this one.
I guess
Yeah.
general remark here is, physically speaking, it's not obvious that must be diffusive. You
Like-
said you're going to introduce something diffusive here,
Right.
but
It will be because of fast derivatives.
no,
It will be because of fast derivatives that is already sitting in.
I don't see a derivative there.
No, the derivative. Yes, I would have to show you
He's
what.
going to introduce a first derivative there.
No, it will
Actually,
be.
it is in the equation. So we have the space derivative. Let's take the mass equation. So if q tilde is a function of the residual of the mass equation, so the residual for me now means, like we saw it as L minus S. So L includes this derivative, this nabla dot
Yeah.
u, and that's why then when we plug it in and put that term in here, that's actually when we have a derivative, because tau times
I
L.
guess Seijo is right to say you could have one derivative, but not necessarily two
Well,
derivatives.
two. There will be two because
So
because,
are you going to
because you
show
already
this?
have divergence. So
So
this
you're
is
going to
called
show us-
Galerkin least square stabilization. What is
Yeah.
done here, and you're just
Okay,
adding
okay.
operator squared.
So that's what you're going to show.
Oh, well, yeah, clearly it's not clear here since you asked this question, but yeah, like it would be, I would have probably to add an addition. Well, actually, yeah, it should be able to visible from here because we have a space derivative multiplied by another space derivative, but yes, if it's my fault
Yeah.
because I didn't put the definition of R. I didn't repeat the equation on this slide.
Hold on. So
Yeah.
it's coming, right?
I don't think so. I thought it was clear from this one, that's why I actually didn't think about putting
Any
it.
advection term will, through this technology, give you something that is advection applied twice.
Well,
which is upstream diffusivity, downstream diffusivity. I'm sorry.
It's always downstream diffusivity. So you never get negative viscosity in short.
no.
And
Oh,
that-
in that sense, no. No.
yeah, that's so
But
that's
This
something.
this
It's,
is
it's
always
not obvious to me either.
Yeah.
Okay.
It's
I mean,
you-
the sign is important. Just because you have higher derivatives,
No, it will be always term like u nabla. So twice u nabla. What
Yeah.
you will get from this.
okay.
Yeah, I can write it
And
down
that's why it will
later.
be
if
always
you're
correctly acting as diffusivity.
I guess physically you're assuming something localness.
No,
If
no,
you
it's-
assume already,
That's
It's
why
all-
very simple.
So let's just take, without even going to VMS, just take SUPG. So where we have L of Q, H, that for us is U velocity. I'm just taking some advection equation, okay, to make it simple, of Q. So this is my L. And I would like to have some stabilization term that is a function of this QH, but it must stabilize. So by what we have here, the stabilization would be a nabla psi after integration by part here, multiplied by some parameter times the residual of this equation, where the residual of this equation is actually, in this specific case, it corresponds to U, the QH. So we have a space operator. Well, in this case, we will actually have a U here.
Yes, and that's the point. Yeah. So you have quadratic form.
So we have a Laplacian here. Dimensionally, this is it would be a Laplacian, let's say, squared nabla of Q. That's why it's actually diffusive. That, yes, like you can see until you plug in some definition of Q tilde here. Like this is not a diffusion term until you define Q tilde to have enough derivatives to be diffusive when multiplied by nabla.
Okay, so make a long story short, if you assume this red box, then
Yes,
you
exactly.
automatically end up with eddy diffusion.
Exactly.
So we have to swallow this red box.
The red box actually is one of the many ways of defining Q tilde, but yes, this is the reason why we would be able to have some Laplacian inside the blue box.
Yeah, I guess, so
So yes,
logic is
it's-
kind of backward. You won't have Laplacian in the end, then you know it will stabilize. So I assume this, and then
Yes,
we can
yes,
rely on
yes,
it.
yes.
Yeah, okay, fine.
And in fact, one more thing, now this is Euler, so we don't have any additional physical viscosity, but if we work with Navier-Stokes, we would actually end up having an hyperdiffusion term, because we would even have some nabla to the fourth of the quantity to be solved for. So we would always have some diffusion that comes from this fact that we are trying to obtain some Laplacian somewhere in the diffusion term. But the idea is that of not simply putting a Laplacian just like that, simply because we know that the Laplacian would have this effect, but to put a Laplacian that at the same time is controlled or knows something about the problem, about the physics that is going on. That's why we use the residual, and actually you have information from the original equation itself in here. So if this entire term is a function of space and is not just uniform everywhere. And that's
The beauty here is you can derive this eddy diffusion term in more, well,
in more what?
I don't know more what,
Okay. Well,
in
This
nicer
ansatz-
ways.
That this ansatz that Q tilde is proportional to the residual. Is there a theory behind that, or is that you could say, I'm just going to choose that because I know it will be diffusive?
you can, well, in reality, you can get to this term by solving a system defined for the Q tilde. And in fact, this tau term also is taken as under the assumption of being the inverse of the original L operator of the equation. So like there are some theories behind to actually get to here. Unlike, it's a little bit like if you derive SUPG, you derive it in a totally different way. But then at the end of the game, at the end of the day, you always get to some term that looks like this. So you get there from different directions, but always there is something behind that gives you this type of information at the end. Okay, so and some ideas, variational multiscale has been applied a lot to incompressible flows, to the solution of the Navier-Stokes equation, to advection, diffusion, reaction equations. A little less literature exists for compressible solvers, and when it does, it's mostly for really compressible flows, where we have shocks or at least large pressure waves involved. So the idea here is to try to see how we can apply this method and see if it really works also when we are in low Mach number, which is the case of atmospheric dynamics. So close this parenthesis on the history of it. Here comes the tau. The tau for the couple problems, the system of equations that we are solving here would be a tau that, well, is a diagonal matrix where each equation would have its own tau. Here, its own tau in reality is not the proper thing to say because they're all the same, but in principle this tau might not be the same for every equation. Here it comes out to be the same because of the type of equation that we are solving, but already you see how in the transport of theta we don't have the speed of sound c involved. That was actually for mostly practical reasons. We achieve better stabilization without considering c in the last equation. For if you do some analysis, you see exactly why that. But the idea is having coupled system of equation where also the stabilization is coupled and changes equation by equation.
And H there is like a nominal grid spacing?
Yes, in fact. And H, there are a few things to say about tau in reality, because tau is not just something that comes out with the VMS. Tau exists in SUPG, it exists in most of stabilization techniques that rely on the same idea of adding some diffusion-like term, where we would like that tau to not be a function of space. Yes.
Simone, would it be possible to include a physical model in this tau?
Yes, in fact, consider that, and there is a very thin line between VMS and LES, for example. I don't know if that's what you were thinking about with your question, but a thin line that comes from the fact that the two ideas are derived in different ways, but at the same time, we can build VMS by purely mathematical means, but to actually obtain, because of the physics, what an LES model would be. It's not the case in what I'm showing right now because of the way I built VMS. Like the way we built it right now, we haven't considered certain terms that would be necessary to be considered if we wanted to have an LES model using using this technique. But yes, you could add physics into this tau in that sense. In fact, like there are some studies since the beginning of 2000 where people are starting to work on this a lot, especially for incompressible flows.
I suppose this tau is related to final eddy diffusivity coefficient.
It can be related. Like maybe it's not exactly in this case, but
yeah.
Yeah.
Then there's huge literature in turbulence community how to define this eddy diffusion coefficient. That's the way to paraphrase Young's question.
yes.
And
And
are you going to say something about it, or?
well, I'm not actually an expert on LES, and but yes, like this tau. Let's if we compare it more straightforward to a Smagorinsky type of.
Yeah, that's my specific question. That he got H factor somewhere
Yes.
in
So
his coefficient,
yes.
and so straight question: is it consistent with this formula? Or
The answer I would have to look.
Yeah.
I actually don't know enough on Smagorinsky.
and I don't remember, so I can't say.
So yeah, but also consider that in the concept of VMS, this tau is not. It can be very different. It always comes to be some function of velocity of the flow and some function of the grid, but might be written in constructed in slightly different ways. It might have some different coefficient in front. There is not really a well-defined theory behind how to construct tau, at least for VMS. That probably is a little more, I don't know if it's more developed or more known when we go into Smagorinsky or turbulence modeling. But yes, there is some work to be done on tau and on the stabilization itself in general to see if the solution can be controlled and to have an accurate solution.
Well, I guess my point of view would be it would be nice to be consistent, and if it's not consistent, you
Right,
have to
in
show
that
us
sense,
either.
yes, I agree. Yes. Okay, so, and this, just to give you an idea, here I'm plotting the actual shape of that Q tilde. So if we are solving the density current problem, and here, imagine that this is the right-hand side of a symmetric problem. So here you actually kind of see the density current shape. We are not, and I'm not plotting temperature here for the density current problem. What I'm plotting is for every equation, so mass, theta, momentum in u and in x and y direction. I'm actually trying to show you how these q tilde are in reality a function of the solution. They try to jump into the problem only where there are some gradients, where there is some physics going on. When there is nothing going on in reality, the values is pretty much zero. Here the values are normalized with respect to the solution variable. So here as the q tilde for rho is in the plot is q tilde for rho divided by the value of rho in the domain. And so we have some relative measure on how much diffusion I'm actually adding on distributed in space with respect to what I'm actually solving for. So in this case, where density is the temperature is the interesting variable, if temperature was of the order of magnitude, perturbation of temperature order of magnitude of 15 Kelvin, here what we are adding is a q tilde and not the diffusive term. So the q tilde only is of the order of 0.008 with respect to 15. So okay, so we described how to stabilize this finite elements, solution of the Euler equations, but that's not good enough. If we want to solve the Euler equation of stratified flows with the background balanced, with the balanced background, we also want the numerics to give a balanced solution. So it doesn't really matter that we are doing that with the finite differences, and so we have explicitly in the set of equations the metrics of the transformation, and so we might have some errors that come that are important because of the how the coordinates are defined. In terms of finite elements, where this issue is less important than with finite differences, we have another type of problem. If we are using linear finite elements, where we are trying to, where we would like to use Gauss quadrature, so that we use Gauss points inside the element, and we do some linear interpolation from the grid points into the Gauss points in order to then compute the integral, we are committing an error which is actually pretty large when the linear interpolation is applied onto a large variable. So if we have a pressure that does not go linearly with height, does not behave as does not go linearly with height, but with some exponential function of z, especially where the gradient is large, this interpolation would give us a very big error, especially the coarser the grid is. So with coarse grid, this is even more so. So one idea, since we're in reality in this type of problems, we're interested in finding the perturbation of our variables, which are order of magnitude smaller than a background state that we usually know, and we could actually analytically define the background state as to give an hydrostatically balanced solution. The idea is that of computing analytically those large variables, specifically the background state at the Gauss points, and simply doing the classical finite elements interpolation that we need to make for the perturbation variable. So we subtract from the total quantity, we subtract the background state, and in order to commit the smallest error possible in this interpolation. And by doing this, we actually found that for this specific case where we have like this in the classical equilibrium test on the mountain, we obtain 10 to the minus 11 meters per second of vertical velocity, whereas without using this type of technique, at least with the interpolation and this splitting only for the interpolation part of the operations, we would reach something like 10, the order of 10 to the minus 5th, 10 to the minus 4th. So it wouldn't be necessarily considered a bad value either, 10 to the minus 5th, but certainly if the state is in equilibrium, that should stay in equilibrium always. Yeah.
So do you need access to some analytic initial condition, or will this apply to any random real sounding in the atmosphere?
Yes, the point is that if we actually have a real sounding, in fact, thanks for the question, because when we have a real sounding, we don't really know much about some equilibrium on the background. But certainly we can, and please correct me because that's the idea that I had myself thinking, but maybe I'm wrong since you're actually experts in atmospheric problems. And the point is that in that case, we could always think of some background state defined analytically as being a state that is certainly orders of magnitude larger than any type of perturbation I want. So I could always define a background state analytically, subtract it from my sounding, and then do the little game on what I have left. So what I have left would always be supposedly smaller than any analytical background stage that I might take. So that in principle should work in that case as well. And okay, so I would like to point out that this problem is particularly challenging if you have some metrics, and so if you use finite differences in the vertical. The point is that we know that in our case the big problem is not because we are mapping the physical element into a reference element in a finite element type of way, but it's actually because of this interpolation, because I would get the same problem even if I didn't have the mountain. So if I didn't have the mountain and I needed to do this, my atmosphere would still oscillate up and down. Okay, and here just to give you an idea, before even going into the nice and and fun part of clouds forming, we have to test it on three-dimensional problems. Before even going into 3 dimensions, we did some testing on pseudo 3-dimensional in the sense that we have one element in the y direction and it's a periodic on both directions, and we were expecting to obtain exactly the same solution, otherwise something was going on with the code. And then finally we did that with a 3-dimensional warp bubble. So it works, at least it seems to be working in 3 dimensions. Now we can say, okay, it works dry in 3 dimensions, let's see what happens with the wet atmosphere. Wet atmosphere, the set of equations we're solving are exactly the same, except for source term on the right hand side of the temperature equation and a correction of buoyancy due to the fact that we have some water tracers, and then we couple them to 3 water tracers, vapor, cloud, and rain, by considering the fact that we will use some Kessler microphysics for warm clouds only. So we only use, we don't have ice or anything, or graupel or any other water type of water particle. But here I'm writing the system all together, but in reality what we do, we solve the 2 systems separately, and we do it with the classical saturation adjustment technique, where without having to read all of this, is not really necessary. But the point is that we advance the Euler equation first without that right hand side on the temperature. We do the same for advection. All these thermodynamic variables that we obtain from this, let's call it dry solution, even is not really a dry solution, but let's call it like that because we are not considering the equation, the actual phase change. we feed them into some parameterization, Kessler in this case, and what we obtain then is used to correct the thermodynamic variable. So that's the way we solve it. But in terms of numerics, we do exactly the same. We use bilinear finite elements for all of these equations. And we would like to obtain, to simulate something like this. Here, the sky is pretty clear, at least here on the foreground, and we see how some clouds are forming more than actually coming. So they form probably because, not probably, but because we have some sufficient conditions for water vapor to be risen to regions of lower temperature and lower density. Once a cloud forms, if the conditions are correct, it's a self-sustaining process. It starts triggering this big mess, and like this big convective cloud and storm, they all interact with each other, and so you start seeing here some, well, here it's not really visible, but by the colors I would expect to have a lot of rain coming down here, and even more clouds form, and just like they came, we are going to see how with time, after reaching the mature stage of the storm, they just dissipate and everything becomes clear again. So we would like to see if we can simulate this on scales similar to this. Okay?
So is this single day in Barcelona?
What's that?
Is this single day in Barcelona?
No. Oh well, you would see this often by looking at the sea. If you go early in the morning, everything is clear.
Yeah.
And then by noon, you start seeing that. Maybe
Yeah.
not where you are, but
It's more than single day.
oh, this is actually only about. This happens in about 3 hours, 3-4 hours. It depends.
Well, I'm seeing this for more than 1 minute, I suppose.
Oh, this is like the movie is a 1 minute, and this actually
really?
would happen in about 3 hours.
Oh,
Maybe
it's-
more, maybe
it's
more.
just repeating.
So, if we flew with an airplane into that storm, we would probably be able to take a picture like this, where here you are going to see some, once the clouds reach the tropopause, it starts flattening because there is some inversion, and there is no way that we can actually go above that, and so it would be nice to obtain some simulation of this. Now, I would like to actually say first that here the idea was that of seeing if we could stabilize the problem, stabilize this type of equations, also when we have phase change and we have a lot of things going on. We haven't really had the time to really analyze how much of these results reflect reality, but at least just by looking at the results with the eye and comparing to pictures, we think we are on the right track. So this just to say what the idea is behind all this. And here, same thing. Actually, this type of problem is slightly different. We in the previous problem, the convective storm forms because we have some thermal forcing, and we have the water vapor that is on the lower layer to be lifted, and this cloud form. In this case, the forcing comes from the fact that we have a mountain, so we have some wind. So certainly we might have some vapor on the lower layers. This vapor is lifted up to the higher layers, and we obtain a different type of cloud. So the forcing is different, the result is different, but we are using in this specific case, this one and the previous one, exactly the same sounding. So we took a sounding, which is a real measurement, and we forced the problem with the mountain. In blue, we have rain here. This is precipitation.
It's an open system.
Was that?
System is open. Or what is bounded?
Oh, yes. I have, no, it's periodic in X and Y, and we have a sponge layer. We need to have a sponge layer on the top, because without like the big gravity waves that would generate would actually affect my solution too much. I might not even ever get to having a stone developing if I don't have the sponge, and it's simply free sleep on the ground.
And what's the domain size?
this is 80 kilometers. No, this, I think this was smaller. The convective storm, this one was 80 times 80 in both directions, and 24 kilometers in height. And if I remember well, this actually is the same. Now I have my doubts simply because this mountain seems to be pretty big to
And
be
you
within an
put
80.
bubble initially.
There is a bubble in this one, but there is no bubble in here. Here the forcing all comes from the fact that,
You have a background wind.
yes. Well, in both cases we have a background wind, but here the wind,
Yeah.
Would
well,
go through the
that's what I
mountain.
would say. Yeah.
yes, yes. In fact, the bubble here, well, the atmosphere, in the bubble here, unlike the classical warm bubble in a neutral atmosphere, you don't really see this bubble developing and going up. Like you see kind of oscillating, but that oscillation is good enough to force the water vapor on the ground to be lifted enough and trigger the entire process. When it felt like this, the entire process, I go very quickly on this, but this is how it forms. So we have some background state, and this is a pressure, log pressure, scuti, temperature, thermodynamic diagram, usually to see what thermodynamic conditions we have in a measurement. And we are only able to have some convective storm forming when this red area between a wet adiabatic curve and the dry adiabatic curve is sufficiently larger. This is called convective available potential energy, so it's energy that must be in the atmosphere along the column for the cloud to form. In fact, once the cloud starts forming and we start following a certain particle that originally was on ground, let's just take one part of the volume and we start following it. So we lift it up to a point where temperature and pressure allow for condensation to occur. So condensation starts occurring, the cloud starts forming, and we start having this vertical motion, and my particles start moving, okay, along the dry adiabat. But you see that the area decreases because we are actually burning energy we are having a cloud forming at the expense of this energy. So this area gets smaller and smaller at the mature stage when it actually starts raining, and then it starts dissipating. So we don't have enough energy anymore to even have new cloud forming on the ground. This is pretty much what you were seeing. If you were following this diagram during the time-lapse video, you would see more or less this concept behind. And so we had to compare our results against some literature, not just by looking at pictures. And so we took this paper by Gabershek of 2012, Monthly Weather Review, where they did some nice analysis on how the solution depends not only on the grid spacing, but also on the interpolation, on the order of interpolation, because Gabershek used high-order spectral elements, and they did this analysis. We use first order, but we wanted to obtain equivalent grid spacing. We wanted to obtain more or less the same solution. This was a good example to use to compare, because they also use finite elements. It's a different type of finite element, but still finite element solution. Going from left to right, we increase the resolution. And because of the microphysics, we cannot expect the solution to actually converge into the grid, but we might see maybe some convergence once we go at very fine grids, but we can't really expect that because of the microphysics and the parameterizations behind the microphysics that might be grid space dependent. So, but still, by knowing this a priori, we are happy with the results as long as they compare well. It's not just a matter of comparing the cloud. Here, this cloud is a contour of about 10 to the minus 5th kilograms per kilogram of dry air. So this is a mixture ratio. Then we have in a color shading, that's potential temperature, equivalent potential temperature. And to actually give you an idea, here you probably don't really see that much, but there is a difference between this shading and this one. Here, the shading is also white contour lines, whereas here the contour lines are black. So black contour lines for Gabershek means positive potential temperature perturbation, and negative when we have white contour lines, and so the white for us corresponds to the blue shading. The white for Gabriel shell corresponds to the blue shading for us. What is this blue shading? This is a density current that forms. When it starts raining and we have some rain evaporation in the upper layers and rain start falling, for mass continuity, for the continuity equation, we have some air that is transported with the rain itself, but it's also cold air, cold masses of air that drop down and form these density currents on the ground. So here we would have, I'm not representing it here, but the rain would be concentrated in this region, right here, and that's why you have this specific shape of the density current. And finally, to also have an idea, numerical idea, quantitative, we wanted to see if the amount of precipitation is comparable, at least seeing that within 6,000 seconds we cannot expect to have 2,000 millimeters of accumulated rain, but in the order of magnitude of 100, and that's in fact what we obtain. Because the solution does not converge, also the amount of precipitation changes with the increased resolution. And this is pretty much what happens. So I put in here, you see a skyline of Barcelona, just to give you an idea on the sizes we're talking about. So here this is the city, about 15 kilometers in extension, and we are on 24 kilometers in height in this domain. So let me play this again. So this is the city where we have some perturbation, a storm start forming, and then we have in dotted lines, we have rain that start coming, whereas these blue, almost horizontal lines are the isolines of water vapor, okay? And then we see clearly how some gravity waves start propagating, and our cloud, once it reaches the tropopause, expands and it tends to move far away from the original point. And this storm happened in about 10,000 seconds, so it's comparable to the original, to the video. But now, since the title was three-dimensional simulations, so here a three-dimensional simulation. The left panel is looking at the problem from above, on the XY plane, and here is just a skew view. We have the arrows indicate a wind shear. It's kind of a weak wind shear, and we trigger the entire motion with a warm bubble in the middle of the domain. So the clouds start forming. I'm not representing rain here. It's just the cloud to give you an idea on how actually the cloud, once it forms, it's not just steady and it stays there, but it starts forming and evaporates again, it dissipates, and so happens on the top. Like you see some color shading changes. The shading on the gray, like you see at first, it takes a little bit to trigger, but once it's done, then that's it. It explodes upwards, but you see how there are very important updraft in the middle of the cloud. The updraft that actually, even when we reach the tropopause, tend to move even above that. And yeah, I think it's pretty cool to see the cloud forming like that.
It looks like your mesh is stretched.
Yes. Yeah, I stretched the mesh because I knew where the perturbation was, and I was expecting the cloud to form in a certain region. So to have less grid points but enough resolution in the center, that's why I stretched it. So it's like this cross center here, but that's the only reason. I didn't really do any study on different type of, well, I used two different grids to see is also in 3 dimensions. I would get that effect of having a solution that kind of changes. In fact, the shape remains pretty much the same, but what changes is the distribution, is the kind of how extended the cloud in reality is. So I did 2 different studies, but the idea of stretching that was just that. And the vertical, what I didn't change was the vertical grid spacing, the order of 200, the order of 300 meters in the vertical, and this finest grid spacing in the center on the horizontal is the same order of magnitude, it's about 300 meters per side. And And that's pretty much it. So the idea here was to see if we could stabilize the Euler equation, the finite element solution of these equations, without adding anything that could be considered as a real artificial diffusion in the classical sense. In classical sense, meaning constant and uniform diffusion with values of the coefficient that might be very large, up to above physical type of values, and to something that could already be considered some turbulence type of closure. So the nice thing here, I think, is the fact that we have a method that just numerically can stabilize the problem, but by adding sufficiently small diffusion that would not really affect the physics. So in the results I was showing in the comparison with Gabershek, in Gabershek, I think it was a hyperdiffusion that was being used with 200 square meter per second of coefficient, and so there was some, it could be seen as having some turbulence closure in there. In this case, by having very small values of the order of 0.0 some small value of the of the entire stabilization term, we can separate the physics from the numerics. So solve the equations, stabilize them, because we need to stabilize them with sufficiently small diffusion, and then if we need to add some turbulence modeling in some other way, well, we can do that by having that fully disconnected from the numerical solution, the numerical technique that we're using. So that's pretty much the idea and what I would like to obtain with this type of method. And then, as I said, I didn't do any type of mass conservation analysis. I didn't analyze the positivity, monotonicity properties of the technique. I already know that VMS on its own is not monotonicity preserving, so all the negatives within the Kessler parameterization were actually chopped off, and so on and so forth. But the idea would be going into high order and using some LES-based hurricane simulations for this type of problem. So based on this technique, not actually for this type of problem. And then there are some readings on like we submitted a paper on the wet results. The one on the dry results was accepted a few weeks ago on VMS specifically for the Euler equations, and then everything else was pretty much done following and comparing results against the literature. And I'm done. Thank you.
There are a lot of questions already. Any further questions?
Just a technical question to the last example that you showed about this idealized cloud simulation. That was just forced by an initial perturbation, is that?
Yes.
So there was no continuous forcing except the initial perturbation.
Exactly.
So you just took a conditionally unstable profile with respect to moist convection.
Yes. Yes. Yeah. In fact, the background state actually is a sounding, and then I just put a big bubble in the middle that would force a perturbation on and potential temperature only. And that's the way it was forced.
And it's free slip at the surface, so
Yes.
you don't have any friction.
Yes.
No interaction.
You have a very interesting definition of artificial diffusion. Have you tried to look at some measures of the solution that you could characterize what the diffusion is actually doing? In particular, people have, for example, looked at spectra of the vertical velocity.
Okay.
Cross section, kind of in the middle of the atmosphere, the mid-level height. You're looking at the updraft, and moist convection will drive that updraft to the smallest possible horizontal scale, and your filters are going to push that to some scale that's representable on your mesh, your simulation. So people often look at that kind of measure to see what their filters are actually doing.
No, I haven't done that.
So there's a lot of papers that
Yeah.
have looked at this to try to get a handle on dissipation
Yeah, in fact,
in the models.
I would like to do some more analysis on actually how our method is affecting the solution, and also maybe do some, like try to see how much diffusion I'm adding by doing some analysis on the energy cascade, if there is even any, in the way, at least for the amount of diffusion I'm adding. I don't even know how much energy cascade I would have, but yes, there is a lot of analysis that should be done that I haven't done yet.
So, and along those same lines, you showed, for example, in the gravity current,
Yes.
you showed, I assume they were their tendencies or something that the
mean-
stabilization was producing in the gravity current, way back. But that's okay, you don't have to go back to it.
Okay.
But that's different than saying, okay, what's the equivalent effective eddy viscosity that then could be compared with more traditional parameterizations that others are using to put more behind your statement that you're using some minimal dissipation. The pictures look nice, but it's very hard to look at them and actually make a more definite statement of, okay, yes, this is small compared to someone else or not. It's just difficult to know.
Right. Yes. That says yes. But yeah, I mean, certainly, like I think you were. This one you were referring to.
Right. So
Right.
If we looked at another model altogether and plotted the same quantities, they may look very similar.
Right. Yeah, that's possible. Since in this respect, since this case was at least usually because of convergence, but they had this artificial diffusion with a 75 coefficient, 75 meters per second, and I wanted actually to see how, by pretty much not putting something like the analog of that 75 here would be the value of tau, that would be on the order of when it's large. Well, it depends on the grid. So at a constant grid, it goes like the module of probably I should actually look at that.
It's a difficult comparison
Yeah.
to draw any conclusion from.
Along that same line, are you able to run with just a del squared, with the traditional, as you say, artificial viscosity? Because that would make a very nice comparison, this exact same simulation with the del squared and with the VMS, and qualitatively and quantitatively compare and contrast the two and show what VMS is giving you.
I haven't done that, but that would have been probably
May I
first step.
comment on this? So you see, technically, the diffusion that is introduced in all such situations will be just what is written over there, right? It will be just streamline acting diffusivity, which will be always, so in direction perpendicular to flow, there will be nothing, and it will be only diffusing along stream. So it will be, say, killing perturbations that you are producing due to dispersive property of your apparatus, right? Through this, and that's the way how it works. In reality, what is done, it's not really introducing small diffusivity into the scheme, because you see what you're introducing entire operator. So this upstream stuff is balanced by your sources and sink, and it's not diffusivity in a way, right? So you cannot say that it's diffusion in reality. I will explain it later.
It is
okay?
effectively some kind of filter.
Yeah.
No,
it is really stabilization, and it is, if you will analyze what is equivalent to some nice meshes, it will be in many cases like fourth order operator.
But it's always energy sink, right?
Yeah.
No, not necessarily.
Can it generate energy?
Because there is something else added to this. It's not only this term, but there is something else added, and it's balanced.
But if I have a 3D system with a downscale cascade of energy, and my system is stable, and energy isn't building up on my grid scale,
Yeah. It is really sinking, but you
Well,
see there are many tricks.
In that respect, Seijo is right. You
See,
can put
there are
some
many
backscatter
tricks
in wave
or
number
tricks
space. You
behind
can
this.
still running your model.
well, no, but if you're putting it all into backscatter, that's physically not what happens in the system. That's not what I want to do.
Yeah, yeah.
Yeah, maybe not. But
Well,
But you see, it
that's
seems
point
to
I
you
wouldn't argue
that,
with.
that it is this operator which does everything, but it's not the case. There are many things that has to be added to this. And of course, you are doing this in such a way that there is energy sinking. That's true. But due to some residual terms that are omitted.
So I'm not saying that it's purely dissipative, but there has to be some dissipation in the scheme to resolve.
And it is always is.
And if there is some dissipation, then I can back that and get a characteristic viscosity.
So you see, basically this technology is like this. Instead of solving my operator, like A acting on my function equals to 0, you are solving something that is L acting on my function plus tau L squared acting on my function, right? So in continuous sense, it should be the same. You should get the same solutions, but due to truncation, adding this L squared, right? It's kind of dissipative behavior. So it's like Galerkin. It's called Galerkin least square stabilization, or you can have many names depending on how you're introducing this, right? So that's it.
So summary, it's not simple eddy diffusion
No,
formulation.
never,
There's
never,
something
never.
on top of that. I guess my main question, probably open one, will be how to exploit this model in applications. Because irony is, most of the areas or CRM can do most of the basic problems without introducing those things. Basic means something you can think top of your head. So to exploit this beauty in application.
Well, yeah, we would like, well, finite elements, if we don't do something either this way or using some other technique, we need to have some stabilizing method.
Well,
And so we would like
all the CRM areas running are stable, otherwise it wouldn't run.
right, but we would like to have,
We can argue forever it's done correctly or not, but looking at the application, they show something nice. Let's just face it. And as far as I follow the literature, there's no serious issue in visible way. It doesn't mean there's no problem. So point is, you got something much nicer, fine. But how you exploit this beauty in applications, that's...
well, for example, let's say that you go into higher order
Yeah.
and you just use some filter like usually is done. Something like this, or maybe SUPG or other similar techniques, they actually preserve the order of accuracy. They don't kill the order of accuracy of the method. So you want to go to high order and then use a filter and your order goes down. So it's like trying to see if there could be some improvement by the numerics if you want to achieve something with respect to, in this case, accuracy. Or here, there was no analysis on accuracy and the order of the method, since everything is first order. But if we can have some numerical diffusion that, since it's not really in eddy diffusion, and can then be separated from whatever other type of subscale parameterization I would like to use, that would be maybe my justification, to have the numerics separated from the physics.
Oh, that was not my question, but it's fine. Let's
Okay,
talk later.
let's take the discussion upstairs, and thanks Simone again.